Hi, I'm Scott Gardner. I'm the General Manager of the Embedded Vision Alliance, and I'd like to welcome the Embedded Vision Alliance community to a conversation we're having with Larry Getman from Xilinx. Larry is the Vice President of the Processing Marketing Group at Xilinx, and Larry was involved in the announcement of a new product family called the Xilinx 7000 Extensible Processor product family. And so Larry, in looking at the information about the Xilinx 7000 family, it struck me that this part was tailor-made for embedded vision. It seems to be that embedded vision has a mix of high-performance pixel processing, high-level general-purpose processing, and high-speed I/O. So did you have this mixed workload in mind when you did the architecture for this platform?
I mean, it's one of the applications we looked at, definitely, and it's uniquely suited for doing high-performance video, high-performance DSP, high-performance vision, because they have that combination of processor and FPGA. And FPGA has always been really great at doing high-performance DSP functions. So we obviously looked at that, and we've had a strong pull from customers in that direction. And we have several other types of applications, too, that this product fits into.
And so embedded vision was definitely one of those?
Definitely one of those, yep.
Now, I noticed that you didn't call the Xilinx 7000 an FPGA, even though that's obviously the Xilinx heritage.
Yep.
So in what ways does the EPP family move Xilinx in a whole new direction architecturally?
Well, we wanted to be very clear that this wasn't just an FPGA, and that was important to us because if you look at Xilinx's history, we've always built FPGAs and we've put things into the FPGAs, hardened. And this is its own unique class. What we tried to do is build something that's very SoC processor-centric, and that combines the best of both that processor and the flexibility and configurability of the FPGA. So we wanted to make sure that it was very clear to customers that this wasn't an FPGA with just some stuff thrown in. It looks like a processor, it boots like an SoC, but it also leverages Xilinx's world-class FPGA logic, the unified architecture, so we have the same tool flows. So if you understand how to program an FPGA, all that's usable. But really, if you're a software guy and you know how to use an SoC, this is a great product for you.
Okay, and so you call it processor-centric.
Mm-hmm.
So could you describe that in more practical terms of what's really different about this architecture from your previous embedded processors? You had hard cores with a PowerPC.
Yes,
so what's really the main differences?
Well, if you looked at the old cores, like I mentioned, it was really around, you have an FPGA fabric, and inside you would put a processor system. And it was really a processor core itself. And then it was up to the customer to build everything around it. In this case, what we've done is we've hardened those things that are standard in an SoC, a processor-based SoC, the processor, the caches, the memory controllers, the standard peripherals like Ethernet, UARTs. So when you actually power this thing on, the first thing that happens is that processor wakes up. It has its own dedicated I/O, has its own dedicated subsystem, so it wakes up like a processor. It loads up its initialization code like a processor. And so a software guy can even turn off the FPGA logic, power it all the way down. So a software guy can take this, start using it, treat it just like any other ASSP, and then start to extend it with the FPGA logic, the extensible part of it.
So perhaps you could work through that programming model in more detail. So you brought your code over onto the ARM9s, and how would you actually go about extending into the FPGA fabric? How do those actually tightly couple into the CPU pipelines, and how does data transfer happen?
Oh, that's a great question. One of the things you need to do when you're building a product like this is you just can't slap two pieces of silicon together. So we were very careful and put a lot of energy into how do we build the right interface. So what we've done is we've put on 8 different AXI ports that are memory mapped by the processor into the FPGA fabric. The other thing we've done is we've standardized all our own IP on AXI4. We've worked with ARM, the originators of AXI, from the ground up to make sure that there was a version of AXI4 that was optimized for FPGA. So now we've created the hardware hooks to connect into the processor through these AXI ports. And we've also created the infrastructure with our IP and our tools and everything else that the customers can then hook up IP into that easily.
And all of these pieces of IP hook up in a standard way? So
they hook up in a standard way. So if you understand how the ARM AXI4 interface works, and it's something which someone can go and grab and understand and look at quickly. And they're not having to learn this new type of bus interface, new type of IP. It's something that's really standard out there, and that was important to us.
And there might be these peripherals that already exist on that bus that they want to move over from an SoC, but now have it in this programmable fabric.
Exactly.
That'd be great.
And they can understand it much easier, yes.
So I've heard Xilinx talk about an inflection point that's happening. At 28 nanometers, the cost to develop an ASIC has just become astronomical. And so could you describe really some more detail about that inflection point, and also explain to me, where do you think Xilinx is filling this void? What is going to be the dynamic of how customers go to market and how they're going to be using the Zynq family or your other 28 nanometer FPGAs?
Yeah, this is a really a global play for Xilinx and the FPGA vendors. And if you look at it, costs have gone up astronomically over the years. And it's not just about math sets. It's about the fact that you can put so much logic into these devices that debugging it and bringing it up is a really difficult process. So now we've reached the point where FPGAs and the ability that they offer at 28 nanometers really gives customers the leg up, where they can start to put in their systems, their designs. They don't have to compromise on the performance and the amount of logic they can put in. And what we've done, we've taken it even a step farther with the Zynq product line. What we've done is we've hardened the equivalent of over 11 million ASIC gates that we've already hardened for customers. And if you look, most SoC ASICs that are out there,
And a lot of those are in the ARM cores, right?
and ARM is one of the most popular cores out there.
Right.
Yeah. And if you look at most of those that are being built, they have a processor subsystem, they have memory controllers, they have peripherals. And what we've done is we've taken away the risk and the pain of building that themselves. And then we've given this FPGA extensibility that can go anywhere from 400K ASIC gates up to 3.5 million ASIC gates is what we give from the range of products that we have, which is quite a bit. If you look at it, they've almost 15 million ASIC gates in the largest part.
Well, what impressed me is if you look at the range of the family, so you're starting at a 2-watt part at sub $15, and even your lowest end part has 58 gigamax of performance on the DSP side. And then I guess at the high end, I don't know what the power and pricing is, but I assume it's higher. But the performance, it's up to almost a teramac of performance on the DSP side. It's incredible.
Yeah, and we've tried to build a range of products because our customers look at it and they want lower end products with, even though we say lower end performance, it's still an amazing amount of performance at a good entry point on price. If you look at driver assist, they want things for the more cost-effective entry point vehicles. But they want to be able to scale it up for those more expensive vehicles and add more and more functions. So we've looked at creating this range of products all the way up to the largest ones, which can handle massive amounts of video traffic, really high-end standards, custom broadcast, that sort of thing. So we've really given that customer a range of choices.
So I guess this maybe gets to our last question. Looking at this range of devices and performance levels, so could you give us some ideas of some places where you think the new Zynq family is going to fit?
Yeah, we've actually, as you mentioned before, with vision and video applications, we're getting a very strong pull there. Driver assist, of course, that's one of those type of applications. We're seeing a very strong pull from the military. You know, I've joked that the driver assist and the missile systems requirements are looking more and more similar. And I just recently got back from Germany. I think it's the fact they drive so fast over there. But if you look, the requirements for performance and processing have really gone through the roof in the last couple of years. And we talk about insatiable bandwidth and the other things driving the FPGA side. And Zynq is really that next step. We really have that combination of control processor and DSP performance.
And all the communication bandwidth to tie it all together.
Yep, you got to get in and out of the part somehow.
Yeah, that's excellent. Well, Larry, thanks for your time.
Thanks.
I really appreciate this. I'd like to encourage all of the Embedded Vision Alliance community to continue this conversation online at embedded-vision.com, and please give us your feedback and let us know what other topics we should perhaps bring Larry back to discuss. Thank you very much.
Thanks.